Good evening. We are looking at now lecture 2 of Power Electronics and EV Drives course. So let me recall what we did in the last class. So we were basically looking at what is the importance of power electronics. So we said power electronics is an enabling technology in terms of inculcating sustainability in our life. So what we mean by sustainability is to have as much comfort as possible, but without really endangering the comfort of the next generation. That means we need to have sufficient resources left over for the next generation as well, without really compromising on the comfort at present. So we should have a fairly comfortable life now, and still we should be able to have sufficient resources left over for the next generation. So for this, we need to actually have maybe three specific goals that need to be attained. One is energy conservation in all the processes that we are currently, looking at. So whether it is industrial drives or whether we are looking at heating, ventilating, and air conditioning system, or we are looking at lighting, all these systems, we should be able to run it with less amount of energy and more efficiently. So that means in industrial drives as well as heating, ventilating, and air conditioning system, we should have variable speed drives or adjustable speed drives. As per the temperature requirement, we might have to run the drive at a particular temperature, a particular speed, rather than turning on and turning off repeatedly, or using vanes to simply waste the cold air and sending it out. We should not be doing that. So if we try to do the actual or effective control of the drive, the compressor in heating, ventilating, and air conditioning system by looking at what temperature we want to attain, and if we run the compressor on a continuous basis at a lower speed or something like that, then we don't have to turn on and turn off. That will actually reduce the kind of amount of energy that is being consumed by the compressor. If we are turning on and turning off repeatedly, during starting of a motor, generally it consumes a large amount of current. So that is actually going to tell on the overall efficiency of the HVAC system. Similarly, in lighting system, if we use LED, originally we were using incandescent lamps, then we started using fluorescent lamps. Now LED lamps, what we get out of a 9-watt LED lamp is almost equivalent to 100 watts incandescent lamp. The kind of light what we get out of 9-watt LED lamp. So we are really looking at a huge amount of saving in electrical energy consumed by these kinds of new systems. And for all these things, whether we are talking about industrial drives or HVAC compressor, where it is running on adjustable speed, or if we are looking at LED lamps, for all these things, power converters are really essential. Without power converters, they will not work. So power converters become essential for all these systems. The second thing that we are looking at is, rather than burning coal or fossil fuel and generating electricity in thermal power station, or in gas turbine based power plants, if we can actually generate electricity based on renewable energy, that will definitely reduce the carbon dioxide emission. So carbon dioxide emission will be reduced. So which means we are definitely looking at the global warming kind of getting a little less if we are reducing the carbon dioxide emission. So the renewable energy generation can happen either with solar or it can happen with wind. And solar PV generally produces only DC. So what this produces is only DC. And that DC cannot be directly fed to the grid. So this DC has to be converted into AC. So DC AC inverter circuit is needed, which is basically a power electronic circuit. And this is going to give an AC, which is actually 50 hertz. So 50 hertz and whatever magnitude, if it is single phase AC, it may be 230 volts, 50 hertz single phase AC, or we may have 50 hertz, 415 volts, three phase AC. So we may have 50 hertz, 415 volts, three phase AC. So we can have any one of them that is being produced by the inverter. So for this, again, we are going to require a power electronic circuit. So this is the power electronic circuit we are talking about in this particular case. As far as wind power generation is concerned, we will have a wind turbine, what is here, that will be coupled to a generator. Mechanically, it will be coupled to a generator through a gearbox or something like that. So we are going to have a generator here. This generator, most of the times, will be an AC generator. And this, what this produces will be a variable frequency, variable magnitude, variable frequency, and variable magnitude AC. Because wind is not going to be blowing always at a constant speed. So that is the reason why what we get here will be a variable frequency, variable magnitude AC. Now this has to be converted into DC using an AC DC converter. So that is going to produce a DC, and that DC, what is available, will be converted into AC using a DC AC inverter. So from a variable frequency, variable magnitude AC, we are converting that into fixed voltage and fixed frequency AC. So this is going to be probably at the output, it will be 50 hertz, 230 volts, single phase AC, or it can be again 50 hertz, 415 volts, three phase AC. So this will be ultimately connected to the grid. Whether we are looking at this or this is ultimately going to the grid. So the renewable energy, if it has to be utilized by the grid connected loads, again, we will require power converters. So both solar PV as well as wind turbine based electricity generation will not work properly unless we have power electronics. The third one that we are looking at is, again, for sustainability, transportation using electricity. Rather than using petrol or diesel, which is actually again causing carbon dioxide emission, can we have transportation using electricity? So two kinds of thing we can talk about. One is mass transit system like metro rail, where again we have electricity again supplied from the grid, and it is going to take the power from the grid and it will convert that into variable frequency, variable magnitude AC, and then feed it to the motor. So you can imagine as though this is the engine in the case of metro rail, and you are going to have something called pantograph. And this pantograph is actually touching the overhead line like this, and then it is going to absorb electricity. So this is going to be the electricity which is flowing into this electric car. And we are having wheels here. So what we see here is something like an AC to DC converter. And from that, there is going to be an inverter, and that is going to be connected to the motor. And motor is actually supplying the rotational power to the wheel. So this is essentially the configuration what you see in mass transit system, like a metro rail system, and that will make the entire train run. And obviously, the AC to DC converter as well as inverter both are based on power electronics. So power electronic converters are again at the heart of metro rail system. On the other hand, if we look at battery driven electric vehicle, which are like a Tesla car or from Tata Nexon electric vehicle, all these things basically will have a battery, and the battery voltage may not be exactly compatible with whatever is required by the motor which is propelling the electric vehicle. So we might have a DC to DC converter in between. So this DC to DC converter output will be connected to the inverter, which is DC to AC. And this inverter output will be connected to the motor. So the motor may be a three-phase AC motor. So this is the motor. And this motor will be coupled to the wheels through the transmission and things like that. So ultimately, that is what is giving the propulsion to the electric vehicle. So again, this is a power electronic converter, and this will also be another power electronic converter. So there will be two converters cascaded in all probability in the electric vehicle also, which is battery driven. And invariably, we will have to have control circuits for all of these converters. And the control circuit will determine really whether we are following a particular amount of torque generation and whether we are also making sure that the wheels are rotating at a particular speed. So if you look at the electric vehicle, particularly, we will need power electronic converters for two purposes in those cases. One is for propulsion itself. So we will require the power electronic converters in electric vehicle, one for propulsion, that is for making the wheels move, and the second one is for battery charging. Because if you look at electric vehicle, the battery is the only source of energy that is available. So once it is completely depleted, the battery has to be charged as quickly as possible. So there are fast chargers that are available, which are generally off-board chargers. And we have slow chargers, which are on-board charger. So generally fast chargers are off-board, and this can work in, let us say, an hour or less. Whereas if you look at slow chargers, invariably those are on-board chargers, and they require anywhere between 6 hours to 10 hours for charging. So there is a lot of research going on in battery charging technology as well as propulsion. And for all of them, generally power electronics becomes extremely important. Okay. So now let us try to take a look at the basic building block for the power converter, which is actually power semiconductor device. So I told you in the last class that if we are looking at a basic inverter, if this is my DC source and I want to convert that into AC, what I will require is one switch connected like this, and my load may be here, and another switch connected like this. So we will have the current going somewhat like this. I'm going to have the current go like this through this switch, and I'm going to have the current flow like this. So this is going to be plus and this is going to be minus, and this is how the current will flow when I'm looking at, let us say these two switches are on. So let me call this as 1 and this as 1 dash. So these two switches are on, the current is going to flow in this direction. If I may call this as A is positive at that point and B is negative at that point. So I will have, if I try to look at the voltage or current, it is going to be somewhat like this. It is, if I try to look at what is VAB, this is going to be VAB when 1 and 1 dash are conducting. Rather than that, if I have 2 and 2 dash, two more switches connected here. So this is 2 and this is 2 dash. So this is going to be 2 and this is 2 dash. Now the current will be actually again flowing like this. This will be the current, but it will flow through 2 and it will flow through the load like this, and it will return like this. This is how it is going to be when I have 2 and 2 dash. So when 2 and 2 dash on, blue color path is the current path. And when 1 and 1 dash are on, we are going to have green color path for the current. So you can very well see that A was positive when 1 and 1 dash were on, whereas B will be positive when 2 and 2 dash are on. So we will have VAB positive when 1 and 1 dash are on. A is positive with respect to B, whereas when 2 and 2 dash are on, we are going to have A negative with respect to B. So this will repeat itself if I am turning on 1 and 1 dash and 2 and 2 dash alternately. So when 1 and 1 dash are on, I have to keep 2 and 2 dash off and vice versa. So this is the voltage waveform what I am generating with respect to time. And what I'm looking at is if it is a 50 hertz kind of voltage, 50 hertz, if that is the frequency, 1 divided by 50, which is 20 millisecond, will be the time period. So I'm going to have this entire thing as 20 millisecond. So this will be 10 millisecond, and again this will be 10 millisecond. So we will have the switches turned on and turned off at a very high frequency. So this should be on, 1 and 1 dash should be on for 10 millisecond, and 2 and 2 dash should be on for 10 millisecond. So we cannot possibly use mechanical switches in the place of 1 and 1 dash and 2 and 2 dash. So we definitely need to use something like a semiconductor switch, which can work really, really fast. So the switches 1, 1 dash, 2, 2 dash, they have to be semiconductor switches. And if we are talking about a switch, we should know what are the characteristics of an ideal switch. So an ideal switch generally is going to be uh, uh, offering zero resistance when it is on, and similarly infinite resistance when it is off. So when I am having actually a switch to be closed, so let us say this is the switch. When I close it, it should be as good as a short circuit. And when I open it, it should be completely as good as an open circuit. So it should offer infinite resistance when it is off. And similarly, it should be able to withstand infinite amount of voltage, and it should be able to pass infinite current. So if the rating is really infinity, that is what we want it to be. And it should be able to respond fast. That means I should be able to switch on and switch off at a very, very high frequency or infinite frequency of switching. And we should also be able to have infinite di by dt and dv by dt. Even those should be as large as possible. It should not break down just because the current rate of change of current is very high or rate of change of voltage is very high. So that also should be, preferable if it is possible to have. And size should be small. It should not occupy a large space. And turning on and turning off not only should be done fast, but even for turning on and turning off, it should be controllable, easily controllable. To turn on and turn off, it should be easy. That is also important. Apart from that, the cost should not be high. So all these things are important for an ideal switch. And that is the reason most of the times the devices, if I try to look at it, semiconductor device research always tries to somehow achieve most of these things. So device research aims at all these aspects. To fulfill all these aspects, that is very, very important whenever we look at device research. I am not a device person. I am a person who applies these devices into power converters. So when we choose a device for any of our converter circuit applications, we try to look at all these things. What will be the on-state resistance? What will be the off-state resistance? What will be the frequency at which it will be able to respond? What is the kind of voltage and current or di by dt or dva by dt my device will be able to withstand? And we will also see whether it is easy to turn on and turn off these devices. We look at the size, we will also look at the cost. All of them are extremely important. So if I look at the classification of power semiconductor devices. So there are three main kinds of power semiconductor devices we'll be looking at. One is uncontrolled. You are not going to be able to control the turn on or turn off. Then what is the real usefulness of this kind of a device? Typically, an example is a diode. It will conduct current only in one direction. So if I want unidirectional current from an alternating current means the current will go back and forth. So for example, if I am going to have an AC source and I connect a diode and I connect a load resistance. So this will allow current only in one direction. If the diode had not been there, the resistance will be able to carry current in this direction as well as the opposite direction. So this presence of diode makes it unidirectional current. So uncontrolled device typically is used whenever we want to convert bidirectional current into unidirectional current. The second type of device is semi-controlled or partially controlled device. So in this particular case, you may see that only turning on can be controlled, but turning off cannot be controlled. That cannot be controlled. So typical example of this is a typical example for this kind of a device is SCR, silicon controlled rectifier. So this is generally used for AC to DC conversion in most of the cases. Again, even diodes are generally used for AC to DC conversion. In some applications, they may be used along with the inverter also, which we will come to a little later. The third type of device is fully controlled. So fully controlled device where turning on as well as turning off is controlled. Both are controlled. So typically, we have several devices which fit the bill here. So one is GTO, gate turn-off thyristor. Then we have integrated gate commutated thyristor. We have BJTs. We have MOSFET, power MOSFET, and we have IGBT. So all these things are typically fully controllable devices. So let us first start with, so we will look at the symbol as well as characteristics for each of these devices. So let's first start with diodes. So in the case of diode, we normally look at the symbol of the diode is somewhat like this. So this is anode and this is the cathode, and it is a two-terminal device. So diode is going to be a two-terminal device. So the ideal characteristics for a diode is like if we are looking at positive voltage being applied, it will be able to go to infinitely large current with almost zero drop. And so zero drop is indicated by this. So you will have literally zero drop and it can be infinitely large current. Whereas if we are looking at the reverse side, there cannot be any current at all, and it should be able to withstand infinitely large reverse voltage. So if you look at the actual characteristics, as the current increases, you are going to see that the voltage drop also increases what? So this is how it is going to be. So this is the real characteristics, and this is the ideal characteristics. So if we look at the classification of diodes, there are mainly three types. One is rectifier diode or power frequency, that is 50 hertz diode. So these can work only at about 50 hertz frequency, not more than that. So typical frequency at which they can work is about 50 to 100 hertz, not more than that. And the turn on and turn off time will be as high as uh, a few hundreds of microseconds. And as far as the voltage and current ratings are concerned, they are available almost until 7 or 7.5 kilovolts. And the currents can be as high as 4 kiloampere or 5 kiloampere. So single-handedly, they will be able to withstand a very, very large amount of voltage as well as current. So rectifier diodes are commonly used in very big rectifier circuits where you may require DC power supply, maybe in a power station for the auxiliaries or in big chargers and such things. So you may be able to use the rectifier diode single-handedly to supply almost 30 megawatts of power. It can handle almost 30 megawatts of power. The second type of diode that is again available in the market, which is called as fast recovery diode. As the name indicates, it will be able to go from on to off condition within a matter of, let us say, 50 microseconds or even lower. So they can actually quickly recover from the on condition to off condition, but they are available only at a little lower power rating. So the power rating, probably what is available. So fast recovery diodes can work definitely in kilohertz frequency because they actually recover from their on condition to off condition very quickly. And we look at the rating somewhat lower, so it can be about 6 kilovolts and maybe 2.5 to 3 kiloampere. So they are available at a little lower rating. The third one, which is special application kind of diode, which is known as Schottky diode. So in Schottky diode, generally we have a metal semiconductor junction. Otherwise, in a diode, normally what we have is a PN junction. Let's say this is P and this is N, and these two are going to be having a junction together. And then this is the diode, so we may apply plus here and minus here, and this is how the diode works normally. Whereas here what we have is a metal semiconductor junction, so the resistance is lower. So the voltage drop during conduction, it can be as low as 0.3 volts or something. Whereas in rectifier diode, it can be as high as 0.7 volts if it is silicon-based diode. And if it is germanium-based, it will be even higher. The same will be the case with fast recovery diode also. We'll have almost 0.7 volts as the voltage drop during forward biasing condition when it is conducting. Whereas if we are talking about a power supply, which has only the output as, let us say, 1.1 volt or 3.3 volts or 5 volts, out of that, 0.7 volts is a good fraction. We don't want so much to be eaten away by the diode itself, and that is the reason we don't use silicon diode, which has zero point 0.7 volts as the voltage drop. We tend to use Schottky diode, which is 0.3 volts or even lower as the voltage drop, so that a large portion of the output voltage is not eaten away by the diode itself. So in Schottky diode, the ratings available are pretty small. It is only about 300 volts and it is available for a few tens of ampere. Not very, very large rating. Those are not available. And another thing is when it is reverse biased, that is when the anode is given a negative voltage and cathode is given a positive voltage, leakage current can be high. Because the resistance itself is small, generally the leakage current can be high. So Schottky diodes are mainly used only in power supply applications, mainly to reduce the voltage drop during conduction. And they are costly and they are not available for extremely large ratings. They are available only for limited rate. Okay. So much so for diodes. Let us now try to look at the second device, which is silicon controlled rectifier. So silicon controlled rectifier, the major difference between a diode and a silicon controlled rectifier is it is going to be having three terminals. So this terminal is anode, this terminal is cathode, and the third terminal is gate. So only if you give a positive current into the gate, only if the device is forward biased and there is a positive current to the gate, only then this particular device will start conducting. So if I am having an AC and if I connect a diode, then, and if I connect a load here, I will have actually the supply voltage, if I may call this as Vs, the supply voltage will be somewhat like this. It is going to be maybe a sinusoid like this with respect to time if I plot. And if I try to look at what is the voltage across the voltage across the load will be only, the current will be carried only in this direction. So only during positive half cycle, this will be the voltage across the load. Whereas in the negative half cycle, I will not have any voltage at all. In fact, it will be zero. Completely, it is going to be zero. So the voltage will be zero during negative half cycle, and during positive half cycle, it will be like this. If I now replace this with a thyristor, I would be able to control at what point this particular gate will be given positive pulse. So I can give positive pulse to the gate only at this point, then I will have the voltage available only during this portion. This portion, I will not have the voltage at all. So I would be able to control the point of conduction, but the point of turning off automatically happens if the device gets reverse biased. That is, if this becomes positive and this becomes negative, automatically this particular device is going to be turned off. So we have in this particular case, when Ig is given a positive value, then SCR will conduct provided it is forward biased. What we mean by forward biasing is anode is positive with respect to cathode. So A has to, VAK has to be positive. Only if this is done, then we call that the device is forward biased, and correspondingly, if we give a gate pulse at this point, then we are going to see that this starts conducting. So if I am having, say, thousands of volts as the supply voltage, this current will be, if I have 1 ohm as the resistance that is connected. So this is 1000 volt and this is 1 ohm. So the current will be 1000 ampere. So if the anode current, if I am writing as IA, and gate current I am writing as IG, generally the thyristor has a very good current gain. It is as high as 1000 easily. So what I mean is, if anode current is expected to be 1000 amperes, even 1 ampere of gate current will turn on the device. So the current amplification factor is very, very good for a thyristor. So although a thyristor and SCR we use synonymously, so in a thyristor, the major advantage is the gate circuit can be really, really small. It will not be of high power, although anode can carry a very, very large current. The typical ratings available for SCR are generally, especially even in SCR, there are two types. One is converter grade thyristor or SCR. The other one is inverter grade thyristor. Converter grade thyristors are used generally in 50 Hertz. So their ratings are available again almost at 7 kilovolts and 4 or 4.5 kiloampere easily. So single-handedly, again, they can handle almost 30 megawatts of power. So you don't have to connect many of them in series and parallel if you are talking about just 30 megawatts of power being handled. But you are going to have the turn-off time as high as 100 microseconds easily or more. So you cannot use it if you are talking about a very high frequency circuit. Whereas inverter grade thyristors are generally used for at least until 1 kilohertz. Easily they can be used until 1 kilohertz. So the turn-off time is as low as 50 microsecond or 60 microsecond. So they will be able to turn on and turn off generally at a pretty high frequency. But the ratings available are limited. So it can be available only for about 3 or 4 kilovolts and maybe 1.5 or 2 kiloampere. Nothing more than that. So as the name indicates, they can be used in inverters. But these days, not too many people use SCRs in inverter. They use generally IGBTs or other kind of completely controllable devices. So SCR generally are indestructible. Most of the times, the mean time between failure, we say MTBF, which is mean time between failures. That is almost infinity for an SCR. That means it hardly fails. SCR hardly fails. They will not fail very easily at all. So that is one of the greatest advantages of SCR, although they can operate only at lower frequency and they are available at very, very large rate. And turning off is not at all easy. If at all I am using this in a DC circuit, I have to use an external circuit called commutation circuit to turn off the SCR forcefully in a DC circuit. So if I'm giving a DC supply, the SCR will keep on conducting as long as you're just given a gate current. So one major advantage again is that SCR requires only a short gate pulse. Then it latches into conduction. So the device will latch into conduction. So the SCR requires not only a small current, but it also requires that current in the gate only for a very short while, and the device will latch into conduction once you give a positive gate pulse. And after that, so if we are showing the waveform here, we can just give a short gate pulse here. That is good enough. It doesn't have to be for a long duration at all. And again, in the next positive half cycle, you have to give another gate pulse. So this will be the gate pulse that we are looking at. That is good enough. And that will actually allow the device to conduct from this point until this point, until the end of the positive half cycle. Again, in the next half cycle, it will start conducting at this point and until the end of the positive half cycle. So the gate circuit, the design of the gate circuit will not be bulky, it will not be too complex. That is the major advantage of the silicon controlled rectifier. So the next device that we are looking at is gate turn off thyristor. That is GTO. So gate turn off thyristor is an SCR which will be able to turn on when we give a gate current. So when we give a gate current, let us say I am showing the gate like this, somewhat like this. So when I give a positive gate current, it will turn on. And similarly, when I give a negative gate current, it will be able to turn off. So GTO actually has an arrow going in and arrow coming out at the gate. So this is the gate, and this will be the anode, and this will be the cathode. So these are the three terminals of the gate turn off thyristor. So if we are actually looking at GTO's functioning, if I say this is the sinusoidal signal that I am giving for as input to the GTO circuit, so I'm going to have, let us say this is the sinusoidal supply I am connecting to the GTO, and I am connecting a load here. And between gate and cathode, I have to give a positive pulse for its conduction. So between the gate and cathode, I might have to connect a small positive voltage and a small negative voltage like this. This is how I have to connect it. So that will actually make the gate get a small pulse. So let us say I'm giving a pulse at this point. So when I give a small pulse at this point, like this, then the GTO will start conducting. So it will actually give me an output somewhat like this. Now, it should have turned off on its own. There is no problem. But if I want to turn it off a little ahead of time, I can again give a negative IG at this point and try to turn it off. So that is possible. I should be able to turn it off even before the natural point of turn off. So here, both turn on and turn off, both can be controlled. But the negative current requirement is very, very high. So if I say that I anode divided by positive IG is of the order of 1000, if I try to look at turning off, that is IA divided by minus IG will be only of the order of 4 or 5, nothing more than that. So for turning off, we require a very, very large current. A large negative current is needed for turning off. Whereas if I look at turning on, so for turning on, a small IG will do. So very small amount of IG will do for, the gate current will do for turning on. So the gate circuit becomes bulky because of this large negative current. So gate circuit becomes bulky. This is one of the problems normally we see with GTO. So just to avoid this problem, IGCT was designed or invented. So this is integrated gate commutated thyristor. So integrated gate commutated thyristor is a device which has an amplifier. So it has an amplifier at the gate circuit. So unlike GTO, which requires a very, very large amount of gate current to turn itself off, IGCT will not require such a large current. In fact, IGCT symbol is somewhat like this. You are going to have the same kind of anode and cathode, but here this is shown somewhat like this. So this is gate and this is cathode and this is anode. So the amplifier is shown by this portion. So this is essentially an integrated gate commutated resistor, which will be able to work with very limited gate current for both turning on as well as turning off. So this is commonly used by ABB, which is a company which produces large number of drives. So ABB drives, many of them, drive units use IGCT devices by and large. So this is really good for inverters, making inverters, which can be turned off quite easily with the small gate current itself. So IGCT that way works well with inverter kind of units also. We have another device called BJT. This is bipolar junction transistor. We always add a prefix called power BJT. So power BJT is used in power electronics, whereas BJT normally is used in electronics. So if you look at the symbol of a BJT, for NPN transistor, this will be collector, this will be emitter, and this will be base. Normally, the transistors operate in three different regions. One is cutoff, the second one is active region, the third one is saturation region. As far as power BJT is concerned, uh, we will have literally IB equal to 0 in cutoff region, during which the transistor is going to be off. So the transistor will not be conducting at all. Literally, the resistance visualized between collector and emitter, that will be infinity, very large. Active region is when base current is somewhat small. And during this condition, actually, the resistance visualized between the collector and emitter terminal will be variable. So VCE is generally not small, it is going to be large because a large amount of voltage will be dropped during active region. So when we say the current is IC and VCE is the voltage, the power loss across the device will be VCE multiplied by IC. So this is going to be large. The power loss will be large, especially in active region. Whereas in saturation region, IB is going to be pretty large and VCE drop, which is actually visualized across the transistor, will be only about 0.7 volts or even lower. So the device will be completely on in saturation region. So when we talk about BJT, either we will operate it in cutoff region or we will operate it in saturation region, whereas active region operation will be completely avoided. And active region operation is generally visualized only when we are operating the transistor in electronic circuits as an amplifier. When this is working as an amplifier, only during that portion, it is going to be working in active region. One of the major problems with the transistor operation, especially in power electronics, is normally what is seen is if I am actually having a circuit like this, I'm going to connect, let me show it somewhat like this. If this is my transistor and I am going to use it in a DC to DC converter or a chopper, this is going to be my power supply. I'm going to connect the transistor somewhat like this. And here is where my DC motor or something is going to be connected. So whenever I want the power supply to be applied to the DC motor, then I will apply a base current. If I don't want the DC supply to be applied to the DC motor, under that condition, the base current will be literally 0. I will not apply any base current at all. So if I look at what is the voltage applied across the DC motor, it will be on for some time and it will be off for some time. This will be repeated. So this is with respect to time. I'm plotting what is VDC, voltage across the DC motor. whenever you are going to have the transistor on, I will have complete Vs applied to the DC motor. Otherwise, zero voltage will be applied to the DC motor. So if I try to look at what is IB, this is how IB will be. IB will be again present for this duration, and again IB will be present for this duration. Okay, so this is how it is going to be. And because the transistor is completely on during this portion, it is in saturation condition. And during saturation condition, if I try to look at what is collector current, so the collector current to base current ratio, which is generally known as the current amplification factor, that will be only about 10, not more than that. Whereas if I try to look at it in active region, if I try to look at IC divided by IB, it can be as high as 50 or 100. The current amplification factor will be pretty high in active region, whereas it will be quite low in the case of um, um, the saturation region. So if I'm talking about a DC machine carrying an 100 amperes of current, then I have to pump in almost 10 ampere of current through the base if I want it to be completely turned on. So this uh, transistor is a current driven device. So the base drive circuit will be bulky because we are looking at a very large current being pumped in through base drive. So it is one of the major disadvantages of the transistor circuit. Another thing is the turn time is generally not very high, but protection of transistor, because it actually responds very, very fast, protection of transistor is not going to be very easy. Protection of transistor cannot be implemented with fuse, with a fuse. Whereas if you look at SCRs, they are slow, so their protection can be implemented with the help of fuse. Fuse will melt before SCR gets spoiled. But here, the fuse will take some time for it to melt, whereas transistor will conk out before that. So you will not be able to protect it with the help of a fuse. On the other hand, if I am looking at a transistor, the ratings available are only of the order of 500 ampere and a few kilovolts. So this is the rating available. Because the rating available is only this much, if we want to use in a circuit which is consisting of 1500 ampere load, then we might have to use 3 transistors in parallel. But transistors are generally not good for operating in parallel. If I have 2 transistors in parallel like this, even if there is a small difference in terms of their properties because of small manufacturing differences, what is going to happen is their resistances will be somewhat different. So let us say the total current happens to be 100 ampere. So I want transistor A to carry 50 ampere, transistor B to carry 50 ampere if they are of similar rating. So let us say this is A and this is B. But because of manufacturing differences, I can have the resistance of transistor A happens to be, let us say, smaller than resistance of transistor B. So what will happen is transistor A might carry, say, 60 amperes of current, and transistor B might carry only 40 amperes of current. And because this is carrying 60 amperes of current, this transistor will get heated up. And if it gets heated up, the property of semiconductor is RA will decrease due to getting heated up. Semiconductor property is whenever it is getting heated up, the resistance is going to decrease, whereas in a metal, generally it is the other way around. When it is getting heated up, you will have the resistance increasing. So, because the resistance decreases, the current will go from 60 ampere to say 70 ampere, and this will become 30 ampere. And this will get further heated up, and this will decrease further. So this will go to 75 ampere, 80 ampere, and so on. So ultimately, you see the circuit getting into some kind of runaway, thermal runaway. So when it gets into thermal runaway condition, one transistor is going to be overloaded, the other transistor is underloaded. So the overloaded transistor will eventually, blow off. So you will not be able to use transistors in parallel. So the BJT has multiple problems. One is you cannot use them in parallel. The second one is they are available only for lower rating. The third thing is it's going to be very difficult to protect them because the fuse will not be able to protect it as it is really, really fast. And fourth thing is the base drive itself is going to be a bulky circuit. So because of these reasons, BJTs have not become that popular. In fact, not much research is happening in terms of BJT. Whereas uh, uh, there are two more devices which we'll be looking at. One is MOSFET, the other one is IGBT. So these two circuits we'll be looking at in the next class.